So let's again take silicon as our semiconductor. Now let's say we add boron. We add boron atom to the crystal. So boron, the number of valence electrons is 3. So that means boron is a third group element or 13th group element in the new convention. So in the new convention it is a 13th group element. So let's carry over with the third group. Now in the boron we said that boron have 3 valence electrons. And the 3 valence electrons are in covalent bond with 3 neighboring silicon atom. Now let's consider this boron here. Now the boron is in covalent bond with 3 neighbors. So this boron do not have an electron to share with this adjacent silicon atoms. So there is a vacancy of electron owing to the 3 valence electrons in boron. So we have only 3 valence electrons and we need 4 to form 4 covalent bonds with 4 neighboring silicon atoms. So we have a vacancy of electron. Now we have said that there is a vacancy of electron. So even at small temperature, an electron from a neighboring bond can move and occupy this site, thereby creating a vacancy there. So in order to understand the concept of acceptor, we rather look at the energy band diagram. So adding an acceptor impurity creates energy levels near to valence band. We have seen that in the case of donor, the energy levels that was created due to impurity atom was near to the conduction band. Here it is near to the valence band, and these are empty states. So we have empty energy levels near to valence band. Okay, these energy levels are empty, that was created by the impurity atom. So even at small temperatures, the valence band electrons can move and occupy these sites, thereby creating a hole in the valence band. Since they can accept electrons from the valence band, these impurities are called acceptors. So we are taking silicon as our example and boron as our dopant. And similarly, another electron can move from valence band to occupy this site, so thereby creating a hole in the valence band. So we can say that each boron atom can contribute a hole in the valence band even at small temperatures. So boron contributes a hole to the crystal, and the material now becomes a p-type semiconductor. At room temperatures, the number of holes will be greater than number of electrons, and say at a particular or at equilibrium temperature we have number of holes greater than number of electrons, or we can say that the majority carriers here is hole. So here hole forms our majority carrier. And always remember, there are also thermally generated electron hole pairs, but we have total number of holes greater than total number of electrons. So we have p-type semiconductor. So for silicon, we may use third group element as acceptor impurity. In p-type materials, the total number of holes is greater than free electrons, and at 0 Kelvin it is still an insulator.